whether he solved the problem or not. So this problem is taken from Merriam. The book is in Merriam, 7th edition, sample 7.2. So if you have the book, you have the solution as well, because this is a sample problem. We show this one because it's interesting. So let's see this one. The electric motor with an attached disc is running at a constant low speed of 120 revolution per minute in the direction shown. Its housing and mounting base are initially at rest. The entire assembly is next set in rotation about the vertical z-axis at the constant rate of n 60 revolution per minute with a fixed angle gamma 30 degrees. Determine A, the angular velocity and angular acceleration of the disk. B, the space and body cones. And C, the velocity and acceleration of point A at the top of the disk for the instance shown. Okay. You can read and read again, try to understand the situation. But let's see this diagram. So this is an electric motor. So we have the disk here, it will rotate, you know. This is mounting on this platform. The platform itself can rotate. And then if you see this motor casing, housing, also can rotate left and right. But in this problem, we fix this position. So in order to limit to have 2 rotation only. Otherwise, we have 3 rotations, right? This platform, this housing of the motor, and then the disc. But in this problem, we fix this one. So there is no motion of this housing. We will only rotate the platform and then the disc. Okay. So when you have this type of problem in 3D, just like what Encik Ramlan always said, always shown in the lecture, we try to indicate the body we are dealing with. So let's say that B naught is the fixed body, the world, the ground, if you want, the casing or whatever. Okay, and then let's say the platform is B1. So in this case, the platform and the housing here is the same body. It doesn't move. The housing doesn't move with respect to the platform, but overall, it is moving with respect to the ground. Okay, B1 is moving with respect to B0 with an angular velocity of n. Okay, and then this disk is considered as body number 2. Okay, the disk is moving, rotating with respect to body number 1. Okay, so in this case, we have 2 frame or 2 axes or 2 coordinates if you want. One is related to the fixed axis or F frame, where we are talking about B1 respective to with respect to B0. Okay, and then the other one is body axis, a body frame. So this we are talking about the moving frame. So the disc is body frame, and the platform is F frame. Okay, so let's draw the axis of these 2 frames. Okay, first the B1, which is rotating with respect to B0. So this platform, it is rotating about Z-axis, the capital Z-axis. Okay, so we have the axis Z like this, and then say that to the right is capital X, and then Y. So let's say like this. This is Z, the capital one. This is maybe X, and then the 2D behind the screen, it is Y, capital Y. Okay, and then the body frame, we refer to this disk. So we are going to draw axis on that. So let's say that it is rotating about the small z axis. And then we define, in this case, we define y in that direction from C to A. So this is the small axis, the body frame Z and Y. Okay, so the relation of the axis is like this. So you need to know the relation. In this case, the body frame and the fixed frame, they are not coincide, and they are, one is vertical, and just see the Z here. One is vertical, one is inclined with an angle of gamma here. So gamma, according to the problem, is 30 degrees. So if you see this one, this is the capital Z, this is the Z axis. So we have the K, capital K, which represent the capital Z axis, consists of cosine G, cosine J. So if this is 30, so we have Z equal to cos to this. So I will say this one. So let's say this one is confusing. So I will draw a new one. So this is the Z. Say this is the small z. And then this is the small y. We know that this is 30 degrees. Okay. So the conversion is the K in the capital K is this y plus this projection of z. Okay. So projection of z is, if this is 30, this is also 30 degrees. So projection of y will be cosine 30, small j. Projection of z to the capital Z axis will be sine 30. Okay. So that's what we have. So this is the relation of fixed frame and body frame. The rotation of the platform to the fixed body, B1 with respect to B0, we use Ramlan Kasiran, and some books use capital omega. That one we talked about last week as well. So capital omega, in this case, the rotation is about the capital Z axis, so capital K. So now in this 3D, we need to separate between lowercase and capital. So the capital unit vector indicate the fixed frame. And then for the body frame, the rotating frame, we refer to the small omega. And then the rotation is about the small z axis, positive. So we write small k. Okay. In this problem, the value is given in revolution per minute. We know that one revolution is 2 pi, 2 pi radian. So you multiply with 2 pi and then divided by 60 because we have minutes here. So we have in radian per second. Okay, in the direction of K, capital. So if you want to convert to the body frame, You just multiply this k, replace this k with this conversion. So you have also in body frame, capital J and small j and small k. And then it's stated in the problem, we have constant here, constant. I write constant because to remember, then when we are asked about omega dot, it is 0. Okay, so the question is about omega t. Alpha t, omega t is the angular total that includes B1 and B2. And with respect to B naught, alpha t is the angular velocity, and then it is also asked V1, VA, the velocity at point A, and velocity of A. This is the point A. So what is the velocity of A and acceleration of A with respect to point O, I think. Okay. So for this, if you still remember the class, the lecture of Anche Ramlan, one of the slides contain this one. This one. Okay, so this is a good summary because we are going to use many of the problem with this, the formula given in this page. Okay, I think I talked about this one as well. So this is two configuration. One is configuration like this. We have a body 1 here. This is body 2. Body 1 rotate with respect to this vertical axis. And then this body 2 rotate with respect to the frame axis here. And then we have another case where in body 2, we have another device moving, sliding like this. Okay, so if we compare our problem to this, I can say that this problem can be represented by this. Okay, we have a platform, so this is the platform that is rotating. We have a disk which is rotating. In this case, the rotation is about z. In this case, the rotation is about the axis facing the screen, but it's about the same thing. So we can use all this formula and this formula. Later when we have this problem, we use this formula and this formula. Okay? Okay, so let's wait, someone is coming late. Okay, so let's put this one aside. Now let's calculate the angular velocity. The angular velocity is the angular velocity is the total velocity. Okay, so if we see this formula, this one, so we are talking about this one, the total, including body 1 and body 0, body 2. So we just add this and this. We did some one exercise last time, I think. Okay, we have omega, which is 2 pi capital K, and then we have small omega, which is 4 pi small k. You cannot add because you know the direction of the frames are not the same, the direction of the axis. So if you convert this one to the small k, or you convert this one to the capital K, capital frame, you can do. In this case, I convert this capital K to the small frame, to the moving frame. You have the omega, you have the capital omega, you have the small omega with the same frame in this case. Okay. The angular velocity, you use this one. Okay. So angular velocity is the angular velocity of the frame one, fixed frame, plus the relative motion. Okay, so this one. Since we have capital omega dot and small omega dot is 0 because omega dot is constant, both. So we have only this term. Okay. Make sure that you are familiar with vector cross product, because in the 3D, we have no other ways. We need to use vector. Okay. So when you are asked to calculate the cross product or vector product between capital omega and small omega, between this and this, you can do faster, very fast. Okay, next question. I'm not talking about the answer. Next question is about the cone. The cone is just imagine how it moves, this one. When it rotates, this body housing will rotate, will create a cone. That is this cone. Okay. And then if we see point A, when point A is rotating with respect to this point O, it will create another cone. So this is the small cone. And the small cone will rotate around the big cone. Okay? Okay, now let's calculate the velocity at point A. We know that velocity at point A is here. And we are going to calculate the velocity and acceleration of this point. How to do? The good thing with this 3D, sometimes we just apply the formula. So we have the formula here. I will take out this one. So we are going to use this one. Make sure that you are using the same symbol. For example, in this case, this one is point B. In our case, this one is point A. This one in this sketch is point A. In our problem, this point A is our point C. Okay? Make sure don't just apply the formula without converting to our case. Convert to our case. So we are talking about this is point C, point A, this is point C. Okay. So it means all the formula, this is point A, this is point C, like that. So in the end, this is the formula that we have. Point A, in this case, I calculate with respect to point O. VA, VO plus omega t cross product the position vector. So if you still remember in 2D, the formula is exactly the same. If you return back to the 2D case, the formula is exactly the same. It's not different. And point O is not translating. So the point O is fixed there. It stays there. So we don't have V naught. We have only this component, rotation. Okay. Some of you can do the vector product directly. me, I cannot do. If more than one component, I use the determinant always. So it's up to you. So I do the determinant. You know how to do, right? So from here, I can obtain this answer. For acceleration, again, we use the one in this formula, in this slides. This A and this A. Okay, so if you want to calculate point A, so this is the formula, this one. If you want to calculate point C, this will be the formula. Okay, okay, so see, I use this equation, I rewrite there. Okay, so I have this equation. So acceleration of point A equal to the absolute acceleration of point O plus all this acceleration. If you still remember the 2D motion, plane motion, this one represent the tangential component, this one represent the normal component. Okay, so it's the same. Last time we always write that the acceleration of A equal to the acceleration of O plus the relative acceleration of A with respect to O. And the relative acceleration of A with respect to O consists of normal component and tangential component. So this is the case. We have the tangential component. This is the normal component in the 2D. Yeah? But in 3D, we don't write normal and tangential. We write the formula like that. Okay, so we have all the values. So the remaining is just putting the value. Okay, I will give you this one later. So I'm going to continue with. I want to go fast to the one that you can participate. But I need to show you some. I need to show you some. Is it this one? No, this is fluid mechanics. Let's see. Is it this one? Okay. So this is question in final exam in April 2008. At that time, the code is MEC 421. Now it's MEC 420, right? Okay, so exam. This is the question. So without reading, if you try to understand the schematic, this one. So we have the rod here, bent rod, and on top there is a platform that can rotate with respect to small y here. And then there is a cylinder from A to B, to this one. It's a cylinder, and then a piston. Okay, so this cylinder can rotate, as a matter of fact. But in this case, it is fixed at theta. On the other hand, this piston B can move, translate, going in, going out. Okay, so by fixing theta, we have now two rotation, one translation. Two rotation means this one. So this rod can rotate with respect to the capital X axis. And then this platform A can rotate with respect to small y axis. And then we have the translation of B. Okay, so if we see the previous one, where it is, wait, I will copy again. If we see this one, how to show everything goes together, right? So this one is roughly something like this. Okay, because we have something that can rotate. So this is in this case, the rotation is about X. In this diagram, rotation is about the vertical, but we have one rotation to the fixed axis. Okay, and then we have another rotation to the relative, to the moving frame, small y. In this case, we have the rotation with respect to the axis going out from the screen. And then we have one translation, B. Here we have also one translation. Okay, so for that, to solve that one, we are going to use the formula related to this. So as long as you can relate the problem with the one that given in the lecture, you can solve easily. Okay, so we are going to use this formula with this one, this and this. Okay, we'll put this one aside. So, but of course, first, step by step, you start to understand the problem. How to understand the problem? By putting body index. So say that this wall is body number 0. This rod, you say this is body number 1. This cylinder, you said body number 2. Okay, and then you start to extract from the problem each of the frame. So the fixed frame, which represent B1 with respect to B0, what do you have? That is the rotation here. Okay, the rotation here, capital omega. What is the direction in this case? X. X is represented by capital I. So I write 3I. 3 is given in the problem. Okay, no need to write this one first. Right up to here. And then according to the problem, there is acceleration of capital omega. If you read, let's see this one. You see, the bent arm OA is turning at an angular velocity omega 3 radian per second and an angular acceleration. So there is an acceleration. Okay, if there is no indication of what direction, you follow the drawing. In this case, the rotation is going to the positive X. And then the angular acceleration. It means this omega dot is also in the same direction. Okay, and then if we read again, this P, which is directed positive Y, according to the arrow here, right, is constant. Is constant, no. Constant rate. No, this one is constant rate. Where? A constant angular velocity P, 2 radian per second. So this angular velocity P is constant. This one will have acceleration. So return back to this. You write what is the capital angular velocity with respect to the fixed axis, and then the acceleration also in the y-axis. Okay, and then you go to the P frame. P frame, in this case, is the platform. Where is the axis of rotation? Use that one as the direction of the rotation as one of the axes. If you say that the rotation P here is about this axis, let's name it Y. I put Y because we have the same vertical axis, capital Y. So I put Y there. This direction is capital X. So we put this one as small x. If it's not given, if it's given, just use the axis as given. Okay, so we have. So it means in terms of direction, at this instant, the snapshot, small x is in the same direction with capital X. Wait a minute, I have a call. What is this one? Hello? Waalaikumsalam. Tak ada nama itu dalam di rumah ini. Oke. Join the meeting. No, I'm out from the meeting. Okay, join again. Okay, so where we are. Okay, about selection of axis, frame axis, body axis. Okay, if it's not given, just try, first you locate the direction of the rotation. In the direction of the rotation, put that one as one of the axis. So in this case, the direction of rotation is this, vertical. So I put one of the axis like this. To name it, C surrounding. If the capital around here, there is one similar direction, we use the same, except we use the lowercase, y and x. Okay, so in terms of direction, small x is the same direction with capital X. Small y is in the same direction with y, both vertical, you see. I'm not talking about the location of the origin. This one, the origin is O, this one, the origin is A, but the direction is the same. So I can say that at this instant, capital I is the same with I. Capital J, same with small j. Capital K, small with capital K, small, same with small k. After you write this one, so you can say that 3 capital I is equal to 3 small I. Okay, you see the step to be able to write this to this is by showing the diagram and by telling this one. According to Jiramlan, he will give mark on that. So I will give mark on that as well. Okay. Okay, so why I write with this frame axis? Because later I will combine this with this. Okay, so in order to be able to add the body 2 with respect to body 1, we have the omega from the problem 2j, and then it is constant. So it means there is no double omega dot. And then we have the velocity here of b, which is 1 according to the problem. Let's read again. This is 1 centimeter per second with respect to this direction, to the direction of the cylinder. It means if you convert to the I and J, you see again here, here. If this one, you have cosine in the X, sine in the Y. Okay, you see, right? So I can write is 1 centimeter per second times cosine theta I plus sine theta J. Okay. And then tangent is given, so you know what's the value of cosine and sine theta. And then it is constant, according to the problem. Now let's see the position of B with respect to A. From B to A, It is given 50 centimeter. Again, 50 centimeter is in this direction of the cylinder. So if you write in vector, you need to find the component in the x direction and component in y direction. So you have this. Okay. Now, the question is about velocity of point B and acceleration of point B. Okay. How to calculate? Let's refer to this. Here, point B is this one. So this is our point B. Okay. Even though this one sliding inside the cylinder, this one sliding outside of the rod. So, but it is the same. Okay. So this is point B. This is point A. This is point A. This is point O. This is point O. Lucky we have the same between the sketch and that one. So we are going to use this one. To calculate velocity of point B, this is the formula. Okay, to calculate the acceleration, this is the formula. But to calculate VB and AB, we need to obtain VA and AA. So this is for VA, this is for AA. Okay, so that's how the formula came from. So I'm using that to calculate. So let's say we want to calculate VB. Where is VB? Did I calculate VB? Okay, so this is the plan. I want to calculate VB with this formula. Okay, to calculate VB, I need to obtain VA. I need to know the cross product of this and the relative velocity of point B. Okay, so I will start calculating omega. So this is the omega. Omega in this case is the total omega, body frame and fixed frame, both in the same reference axis. Small I converted already. This is the, you just add the angular velocity, you just add. Whether one angular velocity is somewhere, the other one is another place, as long as they are connected in with something. So the total rotation will be just you add vectorally. Okay, the acceleration, so I calculate the same thing. Never mind. So let's focus on the velocity. Having this one, and then you calculate VA, VA separately. VA is the tangential velocity of point A relative to O. So it's just the cross product between the angular velocity with the distance. The question, which angular? Since you want to calculate what is VA, VA is this point. This point doesn't rotate with respect to the moving frame. It rotates with respect to the body frame. You see, A will rotate with respect to x-axis with this angular velocity. Whether it is rotating or not, point A doesn't change. Suppose that we fix omega equal to 0, but P is not 0, it is rotating, but point A is still there. Okay, so A depends on this angular velocity only. So the velocity of A will be omega capital omega, times the distance from O to A, which is this one. Okay. You have the omega given, you have the RA, and the RA, you just show this one. RA is from O going to A. In this case, from O going to A, I need to go in the X direction by 20, and then I need to go up by 30. So 20I plus 30J, capital. But since we are having this statement, capital can be replaced with small. See, I write in capital first, and then I convert to the small reference. So by doing the vector product between omega and RA, you have this. That is VA. And then having VA and omega t, I can calculate the velocity of B using this formula, the same coming from the slides. So VA given, obtained, omega t you have, RBA is the relative velocity of B relative to A, and then V relative here is the translation velocity of the slider that we have calculated previously, this one. So if you know how to calculate this vector product directly, do it. If you don't know, do the determinant. Okay, so you can obtain that one. Okay, so the same with acceleration. Okay, the acceleration you see, you have this one. You want to calculate AB, so all this formula. Don't try to put everything together. Calculate one component at a time. Okay, so this is what you need to obtain AB. So let's see one by one. Do we have AA? No. How to calculate AA? It is given here. So start with doing this. Don't put this one inside. Headache. Put one by one. Even this one, try to find one by one. Omega dot. Do you have? RA do you have? So do this one first separately. And then do this one separately. And then do this one separately. So to do this, I did 3 or 4 separate calculation. One is this one is this one, and then another one this one, and then the total one. Okay, step by step. That is to avoid mistake and then to earn marks if there is mistake in what we are doing. Okay, so that's what I do. I will not show you the calculation. So I calculate alpha t. So I put everything, and then I could calculate this term because sometimes the cross product I need to calculate separately to make sure that I do the correct one. And then only when we have addition, I put everything all together. So I add this plus 0 plus the result of the cross product. Rarely we do mistake in the addition and subtraction, but we do mistake in do cross product, multiplication, division, and especially cross product. Okay, after that we calculate what is the acceleration of A coming from the formula as well. From here, this one. So basically this is the tangential. This is the normal. In 2D case, this is the tangential. This is the normal component. So again, I try to find each of the value of this. And then I calculate separately this one. And then this one. And then this one. And then in the end, just addition. Okay, that is to avoid mistake. To avoid mistake. And then from there, having everything you put inside. You see, this is a very long one. So again, See, don't go directly by putting all the values. Again, see one by one whether you have the value of each of these, okay, component. So you have AA, you just calculated previously. You have alpha T, you just calculated. Omega T you have. And then see one by one. RBA, you know. Because sometimes if you write everything, you don't write here. You write you wrote this one in the other page, and then you need to refer to the other pages. So sometimes at that time we do mistake. I did a lot like that, mistake like that. So after you put everything, try to calculate each of these components. The one that you need to be careful. Alpha T cross RBA. I do. And then omega T cross RBA. I do. And then omega T cross RBA. Separately. Don't try to do it all in once. That is my advice. Okay. And then this one. So in the end, it's up to you. So I put all separately, and then only when I have to do addition or summation, I put everything all together. So the mistake can be avoided. Okay. Okay. So now I will give you this one as well. I will jump to. I have so many exercises that I have done, but I cannot show you all. I'm going to go to the one where you can participate. Okay. Okay. This one is important. But I'm going to show you as well this one, not to do. Hopefully I can go fast. So this one is taken from exam of MEC 420 last year, 2019. Okay, December. So last year was December, now only in February because of the COVID. Otherwise, it should be in December or January. Okay. Question B, question A, of course, is about descriptive. Explain why, just and so on. And then question C will be evaluate how if you calculate this one. And then the question C will be how if we consider the mass of this rod, for example, what will happen? So you return back to the old equation, see what will be the effect. But this is the main question, 13 marks out of 20 of this. Looks simpler, looks simple. A rectangular steel plate of mass 12 kilogram is welded to the shaft with its plane tilted 15 degrees from the plane. X, Y, capital. Normal to the shaft axis. The shaft and plate are rotating about the fixed Z-axis at the rate of 300 revolutions per minute as shown in the figure. Neglecting the mass of the shaft, determine the angular momentum H naught about the given XYZ axis, the moment M naught exerted on the shaft by the plate at O, and 3, the kinetic energy T of the plate. So by looking to the question, we know that now we are in the kinetic, not kinematic. The previous exercise, it was kinematic. And the question is about acceleration, velocity, and so on. Now we are calculating moment, angular moment, and kinetic energy. So we have in the kinetic situation. So let's see this problem, this diagram. Okay, there is tilted. Try to visualize. Okay, I'm going to this case. I cannot touch the figure. Okay, let's see this one. Okay. This is the situation. The axis is tilted. So if you see my camera, so this is a plate. By right, the axis is perpendicular. So this is the axis. Can you see my camera? Okay. But now it is not like this. It is like this. So the plate is inclined with respect to the axis, capital Z axis, where I rotate. So it means the rotation will not be balanced anymore. Huh? So if you have your car wheel like this, you need to go to make a balancing or alignment. And this is not aligned. You have to have like this. Can you see my camera, right?
Can, Prof.
Okay. So in terms of moment inertia, the one that you have learned with the formula mr square and so on, 1/12 mr square, something like that, that is if the axis is perpendicular. But now it's not like that. It is inclined. So it means that formula cannot be applied to this case. But we can apply if the axis is vertical. Okay? So this is the situation. The axis linked to the plate is what I wrote with lowercase, small x, small y, small z. So that is the principal axis of the plate. Okay, that is the principal. That is the axis connected with the plate. But the rotating axis is the capital Z, capital X, capital Y. Okay, so if I say the fixed axis is the capital Y, the B axis, the body axis is the small one. And then we try to make relation between the capital and the small axis. So this is the relation. X capital with the small x is the same. It means I is the same with capital I. J, the small j here, following the small y, is cosine of the capital Y minus sine of the capital Z. Okay, so I have this one. See whether you can see this relation from this drawing. The same with K. K in the small Z axis, it will be sine of the capital Y plus cosine of the capital Z. You need to see this one, because this relation is the key. Okay, either you write like this or you write like this. Same thing. Same. It's not the same, but you see, if you see this one, now you see you want to see the capital. So the capital Y is cosine of the small y, plus sine of the small z. Capital Z is cosine of the small z minus sine of the small y. Okay, roughly, this is the relation. Conversion relation from fixed axis to the body axis. Either the left one or the right one. So you have to know how to do this. If you cannot see, just ask me. Okay? Okay, the question is about angular momentum. Angular momentum. About point O. Angular momentum about point O. Let's see whether we can find a formula in your slide. Okay. This one. I will copy this one. And then I will copy it here. So this is from the slide of Encik Ramlan Kasiran. Okay, so angular momenta. Momenta is the plural of momentum. Okay, angular momentum. So this is the formula. But we are talking about, what's the question? Oh, Hg, yeah. By the way, see, before that one, let's see, what is the question? The question is angular momentum about the given axis, about point O. So where is O? O is the center. O is the center of mass of the plate, or G. O is G. Yeah? O is G. So I write HO equal to HG. Okay? And then HG is this one by right. As a matter of fact, not that one. In the slide, it is this one. This one. So since we are talking about the center of mass, so we are going to use this one, angular momentum about a mass center G. Hg is Ig times omega. Okay. Ig is tensor. Tensor is matrix. Matrix like this. So we have the diagonal here is the moment of inertia with respect to the principal axis. Previously, I talked about the principal axis. And then the IXY, IXX, IXZ, IYZ, this one, all this one represent what we call the product of inertia. If we use the principal axis of the body of the object, usually if the body is symmetrical, so two conditions, we use the principal axis, we have a symmetrical body, so this product of inertia is 0. So we have only the diagonal. At that time, if we talk about tire wheel, it is aligned and balanced. But suppose that the wheel is sengit with this axis. So, and then when it is rotating, it's not aligned. At that time, we are not balanced. This component product of inertia is not 0. Okay. But having this one is not 0 is difficult because we to calculate the moment of inertia, you know the formula with integral and so on, headache. So what is the idea? Let's find an axis where I can put all this product of inertia 0. So I just calculate the principal axis. Okay. So the principal axis is the one that I draw here. It's small letter X, Y, Z. That is the principal axis. Why? Because the plane XY is the same with the plane of the plate. The Z is perpendicular to the plate. The capital Z is not perpendicular to the plate. Okay? The small z is. So I'm going to calculate the moment of inertia with respect to my B frame. Okay, the small letter. Okay. So this is the moment of inertia with respect to the principal axis of the plate. If the body is symmetrical. So we know the formula in the 2D that previously, right? The Ix is 1/12 of m times the height square. Height square with respect to the x-axis. So like this. I return back here. So if this is the x-axis, the height will be this one. If this is the y-axis, the height will be this one. Okay? I repeat, if this is the x-axis, you want to rotate this plate with respect to the x-axis here. So the height will be this one. So the formula will be 1/12 the mass of the plate times this height square. That is Ixx. If you want to calculate Iyy, in this case, the height is this one. So you need to square this one. Okay, if in the x you square 300 millimeter, if you want to calculate the moment of inertia with respect to y-axis, you square 240 millimeters. Okay, and then for Izz, you square this one square plus this one square. Okay, so no matter how you call it, this one B, this one H, or whatever, or this one B, this one H, but you know, when you want to calculate the moment of inertia of this axis, you need to square the side perpendicular to the axis. When you want to calculate the moment with respect to this axis, you need to square the side perpendicular to this axis. But the moment of inertia with respect to the axis perpendicular to the plate, you square both sides, each one, and then you add. So this is the formula. Half mh square. This one same thing, right? Half 1/12 mb square. So here h is the perpendicular height, perpendicular to the x-axis. B is the perpendicular height to the y-axis. And then z is perpendicular to the plate. So you add b square plus h square. Okay, I forgot to write the unit here. So the unit will be m, and no, sorry, m is kilogram, and then r square is meter square. Oh, maybe I have there. Oh, I have there. It's covered by this one. Okay. Okay. So if I choose that small x, y, z axis, which is the principal axis of the plate, of a rectangular plate, I can write the matrix of moment of inertia, tensor of mass moment of inertia like this. It's all zero. We have, I'm aligned, I'm balanced. So if I rotate, there will be no problem. Okay. So you calculate with that one, with I, this, and omega, you have the omega expressed in the small x, y, z axis as well. So omega in this case that is the omega of the plate. It was initially in the capital K, you see, given. You convert to the small reference here, the moving reference. This is the conversion. So you have 300 capital K equal to this. And then you do the matrix product. You have the matrix tensor, you have the matrix omega, you multiply, you know how to multiply, right? This times that, and then you add, becoming this one. And then the second line, this second line with this vertical line. And then the third line. And then from here, you can write in the vector form like this. So this one and this writing is the same. Okay, so now you have the angular momentum in the moving frame, in the principal axis. Now the question is about calculating in the capital XYZ. If you read again the question, sometimes need to go up, go down, and so on. Okay. The question, if you read, the angular momentum about the given XYZ capital axis. So I need to convert. How to convert? Using this relation. We have the small axis. So multiply, if you find J in your equation, multiply the J with this. Replace that J with this. If you have capital A, small k, multiply with this. Okay? Okay. Okay, let's see. So yeah, so at the time we have this one, so I replace this small j with the conversion factor that I have, conversion factor, and for small k is this one. So I answer according to the problem. This one should be equal maybe, yeah? Okay. Okay, and the moment about point O, again from the slides of the Cheramlan, you have this formula. About point O, it means about the center of mass. Simple. Okay, and then kinetic energy, this one. Okay, I go fast because I want you to do this exercise with me. Okay, so now let's go to our exercise. Our exercise. I will choose. I did many, yeah. I will give you whatever I did, but in this class you are going to do the one that which can be done faster. Let's see, where is that one? I'm not going to show this one, but I will show you, but we are not going to do. Okay, let's see. So this drawing is the one that shown a lot, even in the Cheramlan slides, many of this sketch. Okay, I did this one. I will give to you, but we are not going to do this one. We are going to do something easier. But it's the same. It's exactly the same. Maybe in Cheramlan will discuss about this one in his lecture. So I choose another one. Not this one. I will start with this one. Okay. I take from Beer. So we take from Beer, Hibbeler, Miriam. Those 3% is the good author of dynamic. Miriam, Beer, and Hibbeler. Okay. Let's start with this. Taken from exercise problem number 18.5. So you see, you are going to do, I will guide you. Hopefully, you can finish. Otherwise, I will give you the note. Okay, so this one. A thin disk of mass m equal to 4 kilogram rotates at the constant rate of, this one is omega 2, 15 radian per second with respect to arm ABC, which itself rotates at the constant rate of omega 1, 5 radian per second about the y-axis. Determine the angular momentum of the disk about its center C. Okay, so this is the problem. This is the sketch. Okay, so it's written in small x, small y, small z. But in our class, the fixed axis, we use capital. So I will change this one with capital X, capital Y, capital Z, because this X, Y, Z, it is the fixed axis. Okay, so you see this arm is rotating with omega 1. You answer quickly. What is the direction of omega 1? You answer. Huh? Give me IJK. So what is the direction of, in 3D, there is no more clockwise and counterclockwise, because in 3D, depends where you put your eyes. So in 3D, we need to talk about IJK. So omega 1, this one, what is the direction of omega 1? Tell me, quick. Come on, come on. This is very basic question. Omega 1, what is the direction of omega 1? Nur Sabrina, you want to try again?
I'm not sure because it is located at the Y. Maybe 0.
No. You see, you say something.
The direction.
It is in the Y, so it is in the J direction.
Wow.
You see? Omega 1 direction is positive J. How to know the direction of an angular velocity? Using your right hand. You see this, my hand? Okay. So these fingers follow the direction of the arrows of in the drawing. Follow. So you are going to have like this. You see? I don't know how you see it. Do with your right hand. Follow this rounded arrows with your right hand. Okay? Have you followed? And then?
Yes, Prof.
Where is the direction of your thumb?
At positive Y. So
Positive Y.
Omega 1 is... Yes.
Positive K, positive J, right?
Yes, Prof.
Because your thumb is in the Y direction, so it means J direction. That is the direction of angular velocity. Now the question, what is the direction of omega 2? Use your right hand again. Positive? K, yes, because if you follow the direction of omega 2 with your hand like this, your fingers, the thumb will be directed to this Z direction. So it's positive K. Okay, so it is important because it's not given sometimes. You need to see from the drawing. So from there, I know that the direction of omega is in the J direction, and then the omega 2 is in the Z direction. Okay, so let's see. Now, I'm going to draw just like what is in the lecture. I start by writing the body. I put the body number. So body number 0 is the fixed frame, fixed body. That is the ground. Body number 1 is the one connected but rotating about the body number 0. So this is body number 1. So all this one is fixed. All rotate at A, yeah, with this omega 1. Okay, and then we have another one moving, which is body number 2, this disk. This disk rotating relative to this arm. So the arm can rotate. And then at the same time, the disk rotating. Ramlan got that model with the fan with lighting. That's very good. So you know how it works, right? So it's rotating. At the same time, this arm is rotating. So we have the fixed frame, and then we have the body frame. Now I changed the fixed frame from this drawing. I replaced with capital to be in line with what we learned in the class. So capital. And then I draw the body frame with small letter. Okay. I know the direction of the rotation. So I choose that one as one of the axis. Okay. Since this direction is the same with this, so if this one is capital Z, this one I use small z. And then the remaining axis I will follow. Choose as close as possible with the fixed coordinate. If this one capital X, I put this one is small x. This one capital Y, I put this one small y. Okay, and then I write what we have. B1 rotate with respect to B0 by capital omega direction. As I ask you, you answer omega 1 in the J direction, capital J, because we are talking about the fixed axis. Okay, omega 1 is 5. B2 with respect to B1, omega 2 in the small z axis, 15. But at this instant, all the directions are the same. Z is toward to the left, X is to the right, Y is going up. So I have this. So it means this 5 capital J, you can write 5 small j as well. Okay? The value you gave, so you have the, you read it. And you can take snapshot or you can write the value. M for omega 2. You write this one. So this is the given. Omega 2 is 15. Z, omega 1, 5G. You write. Okay. Now the question. Calculate the angular momentum of the disk about C. Angular momentum. You know momentum is mv, linear momentum. Angular momentum, m replaced by I, v replaced by omega. If we talk about the center of mass, the angular momentum is Ig times omega. Okay. So this is can you see? This one. I don't want to put too high because I have the solution below. So I want you to do. So you can refer to the slides of the lecture, Ramlan. So since the question is angular momentum of the disk about C, this is point C. We know C is the center of mass of the disk. Why C is the center of mass? Because C is located in the center of this disk, right? So that is the center of the mass, of course, by assuming the disk is uniform. Otherwise, it's not there if it's not uniform. but in our case, it's uniform. So C is the center of mass. So C is G. C is G. So you try to find in the lecture slides how to calculate angular momentum about center of mass. It is this one. Now, give me omega t. Omega t. Tell me. Omega t is the total. Total is vector addition of each component. Omega t. Please participate.
I think it's 5J plus 15Z radian per second.
5J plus 15K. Is it?
Yes, I think
Correct.
so.
Omega t is 5J plus 15K. You just add these two. Am I right? Add these two. This one plus this one. Okay. So it is, you convert the capital J to small j plus 15K. This one is not Z, sorry. This is K, small k. Okay, everybody know. I don't know. I hope I'm not teaching only Nur Sabrina. I teach also others. There is another one question previously, Muhammad. Okay, so 2% I teach. Now, my question is about what is the tensor of mass of moment of inertia? Tensor means matrix. This one. Ix, Iy, Iz. This one. So my question is, what is the value of Ix? Now we are talking about a cylinder. Cylinder. For the axis on the surface of the cylinder, I is 1/4. So in this case, Ix or Iy. For the axis perpendicular to the surface of the cylinder, I is 1/2. This one you need to know. In this case, perpendicular is Z, 1/2 mr square. Okay? So this one you need to know. So I need to erase this one. And then I put back this one there. Okay, so we have the value. That one too easy. I don't ask you. I give you directly. Ix, Iy, Iz. So we have omega t, just like what Nur Sabrina said, 5j plus 15k. So I multiply this one with this one. Sorry, this with this matrix product. So it becomes something like this. Now it is not easy to ask you because you don't care. Sometimes that's what I feel from this side, because I don't see you work. Most of the time, all of you silent, maybe 2-3% talk. So by right tutorial is to ask you to participate, but you keep silent. So okay, that's your choice. Okay, so this is the answer. By right, I should ask you how to calculate. Okay, so this is the angular momentum of the disk about C. C is the center of mass. So it's simple. If you know how to calculate, multiply the matrix with a matrix product like this. So the formula is this one. You still remember Ig omega. That is about the center. Okay, so let's go to the question. Next question. So in this case, I'm going to start with 0 with blank. And then every time I'm going to copy. Please participate in this last tutorial, the last chance for you to study with me. Can you read? Can you read this one?
Can, Prof.
Okay. So this is the continuation. This is, we are doing beer problem number 1810. So this is the continuation of the number 5 previously. So now the question is about determine the angular momentum of the disk of the problem 18.5 about point A. Previously, we calculate the angular momentum of the disk about C. So this is point C. Now we are asked to calculate how about the angular momentum about point A. Okay, you understand that question? So if you go to, this is the question, angular momentum of disk about A now. The question is about A. So we have previously calculated the angular momentum about C. So if you open the, where it is, I will show you angular momentum. This one. Wait. I show you the place. This is Ramlan's slide. Okay. So this is the similar case. You have a body here. In our case, you have the disk. And then you want to calculate the angular momentum about point O. So in our case, about point A. Okay. So similar case, we are going to apply this formula. HA equals to HG plus RGA cross product MVGA. Okay. So that is the formula. I'm going to write it here. HA equal to HG plus RGA cross product MVGA. Okay. HG we have calculated previously. HG, the one that we have calculated, equals to 0.1125 J plus 0.675 K, kilogram meter square per second. So this one I put, this one is there. Okay. RGA, okay, you're going to tell me. I will take a snapshot of this drawing. Okay, tell me, what is RGA?
0.45 I.
0.45 I. And now since we are talking about from this frame, let's use the fixed frame. And then Sabrina?
Yes, bro. Sorry, my internet is lagging.
Lagging. Okay, others. Anas, usually Anas talk. Now silent. Previously Muhammad. I didn't see the complete name. I just saw from my handphone, Muhammad. I use 3 screens here now. I have one screen in front of me, one screen on the left of the camera, and then another one screen as in my handphone. So I will try to see what you see me, how you see me.
Prof,
Yes.
I would like to confirm one thing about the HG.
About?
HG.
Yes.
Before this, you said that G stands for the center of the gravity of the object, right?
Yes.
So basically, the HG is located at the rotating, only for the rotating body, or?
You are talking about this HG.
Yes, because
Okay.
just now I quite confused whether we need to consider G at the rotating body or at the what you call this, slider or something.
Okay, fixed body. No,
Yeah.
it doesn't matter. It doesn't matter. G is a point. The point can be anywhere. So like this one, C. This G is C, right? In this case, C is on the disk, is also on the frame. So if you say C is on the disk, C is in the moving axis. If you say C is on the frame, C is in the fixed axis, but both the same. So I write with respect to the moving axis. But since my axis both coincide, the same, right? Small x and capital X. So I can write this one 0.1125 capital J plus 0.675 capital K kilogram meter square per second. The same in our case, this one. Again, G is a point. A point can be anywhere. So you just calculate the moment. In this case, angular momentum is a moment as well, right? About that point. So you just see the distance, something like that. Yeah. And then since the question is about calculating moment of the disk, of course, you focus on the disk. So you see that previously, Hg is Ig times omega. Omega of the disk, total. Ig is scalar, omega is the vector. Yeah, Nur Sabrina, I don't know whether I answer your question because I...
Yes, it answered my question. Thank you, Prof.
Okay, so for now, tell me what is... Where is my mouse? I cannot find my mouse. Oh, this is my mouse. My mouse disappeared. Wow. Oh. This is not the right place, right time. Okay, now I can see the mouse. Now disappear again. Okay, I need to get out from my... Oh, Anas just joined. Okay. I restart my whiteboard. Time is running out. Okay. Okay, I repeat my question. I need to share again, I think. Share window, whiteboard. Okay. Tell me what is RGA? Based on this.
0.45I plus 0.225J.
That is Muhammad. Who is talking?
Me.
Keep talking.
I'm
I need to
Ikwan.
find. Cannot see who is talking. Muhammad Mod. Let's see who is Mod. Amir.
Yes, Prof.
Now I see. So Amir is one. I cannot see who is talking because you are in the middle. Okay. So according to you, RGA is, repeat please.
0.45I plus 0.225J.
Plus 0.225J. capital J, yeah? Unit is meter. Okay. I write in this. Okay. And then the velocity of G relative to A, it is given or not? Okay, it's not given. G is point C. I repeat, G is point C. According to you, what is the velocity of C or G? C. How you calculate the velocity of C? Tell me. How you plan to calculate the velocity of C? You don't know. Okay. Point C is here. At the distance from point A is that one. That will be RCA or RGA. Point C is on the frame, on the arm. The arm rotates with this axis. So for sure, the velocity of C relative to A is the omega 1, which is in the J direction. J direction, right? Okay. Cross product RCA. This omega 1 is the capital omega. Okay. So this one is capital omega cross RCA. Capital omega is omega 1. J. RCA is this one. So at least one. This is the last question. And then I stop. I will not disturb you anymore. I give up. Calculate for me this one.
$2.25K, Prof. Negative 2.25K.
Negative 2.25K.
Yes. So this one is negative 2.25K capital. Respect. I tried to write separately between small k, capital K, and now we decide to use the fixed frame. Okay, I think I will bother you another one. No need. So you have this one. No, you have, right? No, you have, you don't have. You have VGA. Okay. So now I ask you to calculate at 12 p.m. here, RGA cross MVGA. Okay. So VGA is negative 2.25 K. Of course, the unit is meter per second. MVGA, you multiply that VGA with M. M is, what is the value of M? Let me read the problem. 4 kilogram. So you have 4 kilogram times negative 2.25 K meter per second. So you have 9, negative 9 K kilogram meter per second. Okay, that's MVGA. You have MVGA, you have RGA. So now this is the last question. Calculate for me RGA cross product MVGA. Okay, calculate for me this. Those who are watching without doing anything, you can fill the attendance form. The link is in the chat box.
Negative 2.025I plus 4.05J.
I ask you to calculate RGA cross product MVGA. Okay. What's your answer? Negative?
Negative 2.025I plus 4.05J. If I'm not mistaken.
Yes. Negative 2.025I plus 4.05J. Okay, that's correct. Negative, I will show you here. Negative 2.025I plus 4.05J. Yes. So with that, you have all the components to calculate HA, I mean. So you're going to have, so you have HG, you see, you have HG, you have this product. So you just add this with the one that you have here. So you're going to have negative 2.025 I, plus 4.1625 J plus 0.675 K. Wow, the semester end for me now. It was very difficult to teach dynamic because you keep your silence all the time except one or two students. That is the most difficult part, challenging part. Teaching in class is better because I see you, I can force you to talk. But teaching in front of the camera, I cannot force you to talk. That's the most difficult part of online teaching. So some of you sleep, some of you go somewhere, we don't know. Okay, so with that,